This section of the book is a little different from the others. I'm going to go over a couple of things that are really best to do on a graphing calculator or with a computer, in particular with a spreadsheet or some graphics program. So I'm going to do some stuff on the board, but just small cases, and tell you what you would do in a spreadsheet and tell you what a computer does graphically. This section is also different in that basically these kinds of differential equations that I'm going to look at and approximating their solutions using a computer is applicable to differential equations that arise in any way, in any application, if they're of a certain form. And so for that reason, you might think, so he's going to go through a whole lot of applications. In fact, we're not going to go through any applications because it could be anything. And what I really want to get across here is kind of the idea of the numerical method. And part of the point is so that even when you have a computer do it, you have some understanding of what the computer's doing. So what is it that we're going to look at? We're going to have a differential equation, a first order differential equation of a certain form. So I've got written y prime equals m of xy, or we could have used the Leibniz notation, dy dx equals some function of x and y. So it'll be easiest if I start with a particular example, and I want one that's fairly easy to do by hand. So let's look at, for example, dy dx equals x minus y. So this is a fairly simple looking differential equation. If this were x divided by y or x times y, this equation would be separable and we would know how to solve it explicitly. This equation is not separable, and you're not supposed to know how to solve it explicitly. It is a kind of differential equation called a first order linear equation, and so it is known how to solve it explicitly. I want to go ahead and give myself some initial data, and then I'll tell you what the explicit solution is. But it is not our goal today to solve explicitly. It's our goal to see how you can estimate solutions or kind of graphically see solutions without solving the equation explicitly. So the initial data I want is that when x is 1, y is negative 1. A solution to this is not separable. However, you can show that it can be shown. It's not particularly difficult, but it's beyond what I want to do today or in the textbook, that the explicit particular solution to this initial value problem is y is negative e to the minus x plus 1 plus x minus 1. But what we're going to look at today is, suppose you didn't know that. Then how could you estimate the solution to this? Well, what does that even mean, estimate the solution to this initial value problem? Is that you want a function? You want to have something that's approximately this formula? No, right now we mean numerically approximate it, which means that if someone gives you a different x value other than 1, you can approximate the corresponding y value in the solution. So, for instance, we're going to do just something very special, but if you can do this, you can do any problem of this form, approximate the value of y when x is 2. This is our goal. And of course, we'd like to be able to do it no matter what x coordinate you pick. I'm just picking x equals 2 to pick something specific. Now, I've given myself the explicit solution. I've given you the explicit solution. But I've only done that so you have some hope of seeing what the error is in our approximation. The type of problem you really want to apply this to is one where We can't find an explicit solution. Nobody can find an explicit solution. It is easy to write down differential equations that are very ugly, that no one could solve explicitly, and yet, for physical reasons, you're interested in approximating the value of solutions at various x values, so this is the kind of thing you do. What we're about to do is called Euler's method, and it's the easiest method for approximating solutions. The formulas involved are very easy. They're easy to remember. You don't need to really look them up. 10 years from now, without looking in a table, you should be able to, or without looking in a textbook, you should be able to remember how Euler's formula goes. And if you've got a spreadsheet program sitting in front of you, like Excel, you should just be able to enter it, fill down, I don't know, 65,000 lines, which is quick, and get a good approximation. There are more sophisticated methods than the one we're about to use. Most calculators and computers use something called, well, a modified form of Runge-Kutta. The formulas are very difficult to remember, but then the method is extremely accurate, and you don't need, if you were putting it in a spreadsheet, you wouldn't need to fill down so many rows. But what we're going to look at is we're going to approximate the value of y of 2 using Euler's method. And Euler's method is the easiest method. It's just the realization that, well, it's actually just linear approximation. It's that if you remember linear approximation, or even if you don't, I'll tell you what it is. It's that really one way to think of it is it's that dy dx is approximately delta y over delta x. This is more like the differential approximation, but that's the same as the differential, that's the same as linear approximation. If you multiply both sides by delta x, you get the change in y is approximately equal to the derivative of y with respect to x times the change in x. Or what's the same thing if your change in y, if we write y sub 1 minus y sub naught, that would be approximately dy dx of the change in x, which I'll write as x1 minus x naught. Where do you calculate this derivative? Well, at x naught, y naught. So this, whether you remember or not, if you add y naught to both sides, this is just linear approximation. That y sub 1, some y value, is approximately y naught. It's approximately y naught plus dy dx evaluated at x naught, y naught, times this change in x, which is x1 minus x naught. When is this approximation good? Well, when the value of x1 is close to x naught. If it's not clear, I mean that y sub 1 is the corresponding y value to x sub 1. So here, I mean that y sub 1 is the y function applied to x sub 1. Okay, this is linear approximation. So, okay, we could use x naught and y naught, our initial x and y values. So we were given that when x is 1, right, our initial data, it's when x is 1, y is minus 1. So we could use that for x naught and y naught, then use 2 for x sub 1 for our next x value, and get an approximation for y at 2. This won't be very good. This is just, let me write the real solution up here, get it out of the way. In fact, I'll write the differential equation up here with the initial data. Y at 1 is minus 1. The real solution. So I'll say it. I may say this a couple more times, but in general, these approximation methods are something you want to use when you can't find the explicit solution. We're just doing that case so that I can talk about putting error columns in a spreadsheet or in a table you do by hand. Y equals minus e to the minus x plus 1 plus x minus 1. As an exercise, you could, of course, verify that this is a solution to this initial value problem. when x is 1. You get e to the 0 here, so that's 1. So you get minus 1 plus 1 minus 1. Yeah, that's minus 1. And then you verify that the derivative of this equals x minus this. That's easy to verify. But so what do we get from linear approximation? Well, we get the value of y at 2 is approximately the value of y at 1. So that's y naught plus dy dx at, so I'm using that x naught is 1, and this is y naught. Y naught is minus 1. So this is minus 1. We're evaluating this at 1 minus 1 times the change in x. Well, we're trying to figure out what's happening when x is 2. We start at x equals 1. So this is what linear approximation tells you, but we're trying to apply that to a solution to this problem. In particular, a solution to this differential equation, but then dy dx is y prime, and it should just be x minus y. So here, you can fill in this part. We get that y at 2 is approximately minus 1 plus, and then you put in x naught minus y naught times this, which is just 1. And then x naught, so this is minus 1 plus, x naught minus y naught is 1 minus minus 1. So we get 2 minus 1, we get 1. So our approximation for y at 2, using linear approximation, is that it's 1. That's really not very good. You can plug in that x is 2 up here, and you'll see that this approximation isn't very good. And you wouldn't expect it to be very good because linear approximation is supposed to be a good approximation when the x values are close together, and 2 is not very close to 1. And of course, very close is an imprecise term, but you can have this feeling, yeah, maybe if only 2 were closer to 1. Well, so what can we do? Well, we can use linear approximation in smaller steps, but more of them. So you kind of picture this as you're starting at x naught is at 1, here you are at x naught, and you're trying to figure out the value of y down here at 2. And we just did linear approximation and kind of jumped from the value here to the value here. Well, you could divide this into subintervals and maybe go to 1.25 and then to 1.5 and then 1.75. So that the difference between each x coordinate is 0.25. Now your x values are closer together. And you could try linear approximation to go from here to here, and you would expect that approximation to be better than this one because 1.25 is closer to 1 than 2 is. And then you take our approximate our x value here and our approximate y value and use that in linear approximation to figure out the approximate value of y when x is 1.5. And then you keep using linear approximation to go on. Now, even if your error is smaller in going from here to here and smaller in going from at each step, it's possible that the cumulative error, all right, so you go from here to here and you approximate the y value when x is 1.25. Then you use linear approximation to go from here to approximate the y value here, but you only start with approximate data here, so you've got 2 better approximations instead of 1 worse approximation. It's conceivable that this gives you something worse, but generally it does not. It's usually better to take more smaller steps and do a series of linear approximations. And this is what Euler's method does. So, and that's it. That's all there is to it. It's linear approximation over and over again. So how does Euler's method go? It's just, you have a sequence of x values and a corresponding sequence of y values. So what do? You decide how many subintervals you're going to chop. So you start at some x coordinate. which here is 1. So maybe you start with some initial data that looks like y at some initial x value is some initial y value. I've called this A, and only so that I can say we're trying to approximate. Suppose we're trying to approximate y at B. So yeah, you go ahead and call this A, which for us was 1. You also call it x naught, thinking of it as our initial x value. So you start with x naught, and you want to go to out here to B in steps. You pick some number of steps, so some number of subintervals. Like, and originally we just did one subinterval. We went from 1 to 2 in one step. Now I want to do it in 4 steps. So I pick a number of steps. Pick in the number of, it's usually called steps, but it's also the number of subintervals, whichever, the number of steps. Then you want to give a name to the amount that x changes each time. So if all our steps are the same size and there are n of them, the change in x each time, delta x, is b minus a, the distance between a and b, assuming b is greater than a, divided by the number of steps. If b is less than a, this is still your change in x. It's just negative, and I shouldn't say it's the size. It's kind of a signed size. So you pick a number of steps that you're going to take to go from the x value where you start to the x value where you end up. So for us, in our example, this was 2, this was 1, and we did one step so that delta x was 1. But now we want to do, well, at least by hand, I want to start doing the case when n is 4. So what are we going to have? So we're going to use 4 steps in our example. So let's use 4 steps. So that delta x for us in our example again is 2 minus 1 over 4. So that's 1/4 or 0.25. And so, as I said, you have those 5 x coordinates. You start at x naught equals 1, and then you go up 0.25 each time. So 1.25, 1.5, 1.75, oops, except 3, and x sub 4 is 2. So if you've done things right, when you get to x sub n, your number of steps, you ought to be at the b that you were after. This is x sub n. You ought to be at the value of x that you were after. And what we'd like to do is calculate a series of approximations, or a sequence of approximations. We start with a y naught. We know the y value that corresponds to x naught. It's given to us in the initial data. It's minus 1. But then we need to calculate our y approximations at each step. And each time you just use linear approximation. So what we're after we want y sub 0, y sub 1 through y sub n. So in this example, this will be through y sub 4. The approximations that we get from successive linear approximations. I should emphasize something, a notational conflict that I introduced a minute ago. These y's are approximations. So y sub k is approximately the value of y at x sub k. It is not the actual value of y at x sub k. In general, we wouldn't be able to tell you the actual value of y at the x sub k's. if we started with a differential equation for which we didn't know an explicit solution. Now I gave us an explicit solution, so we could calculate the value of y at x sub k, but what we're trying to calculate by Euler's method, which that's what this is, iterating linear approximation is Euler's method. We're going to get these y sub k's approximations to the y of x k's. By this I mean the actual value of a solution, so y of x is an actual solution, and so y of x sub k is the actual value of a solution at x sub k, and that's approximately what y sub k should be. So what does our formula look like? It just looks like linear approximation, except now we do it to a sequence of xk's and yk's. It's that each y sub k, I'm going to write equals now because equals, this is Euler's method, that this is y sub k is equal to this, but what Euler's method gives you is an approximation. All I'm saying is this thing that we're calling y sub k is equal to what I'm about to write, but y sub k, or y sub k plus 1 is just an approximation to the actual value of the solution. So you take the previous y value that you found and you add to that the derivative at the previous x and y values that you find times the change in x, which is actually this uniform delta x that we wrote, b minus a over n. But now you use that this is a solution to the function that y is a solution to the differential equation that we started with. And the differential equation we started with was dy dx equals some given function of x and y, which means you can put that in here and you get y sub k plus this function m evaluated at xk, yk times delta x. And so this is Euler's method, that each y value is the previous y value plus the function that appears on the right-hand side of your differential equation times delta x. And that's all you do over and over again, and this is easy to put into a spreadsheet and fill down. So, for instance, in our particular case, each next y coordinate is the previous y coordinate, or previous y approximation, plus, in our case, this m of xy is x minus y. Right? We had dy dx equals x minus y. So this function right here, you replace the x by x sub k, you replace the y by y sub k, is x sub k minus y sub k times, and if we're really doing the case where a is 1, b is 2, and n is 4, then as we said already, delta x is 0.25 or 1/4. Let's see, to do it by hand, do I care whether it's, well, let's just go with 0.25. So this is what you use over and over again, or in our case, 4 times. So let me set this up in a table, and it'll be kind of set up for me to talk about what you would put in a spreadsheet. So it fits nicely in a table, whether you do it by hand or on a computer. I like to have, different people put different things for these column headings. They have different columns. Some people put more columns, some people put less. It's not terribly important exactly which columns you have for Euler's method. But the columns that I like to have n, so k, we'll have k, which step of Euler's method we're on. We'll have x sub k, we'll have a y sub k column, and I like to have an m of xk, yk column. And then if you're doing an example where you have the actual, where you can actually produce an explicit solution, then for comparison you might like to have the actual value of y at x sub k. So this would be the actual value of the solution at your corresponding k value, so your corresponding x sub k. You could put the error in a column. Different people would call the error different things, or could use slightly different things. Like you could take the actual value minus the approximation. So that if the approximation, let's see, maybe a lot of people probably take it the other way. Y sub k minus y at x sub k. I like to put an absolute value so it doesn't matter. So my error is, if my error is always greater than or equal to 0, and if my error is 0.15, I don't care whether it's plus or minus 0.15. Some people would. Some people wouldn't put in the absolute value signs. I've kind of run out of room, but I also like to have a percentage of the error column. Maybe I'll stick that here, but you don't have to. But I kind of like to also have a column that's, so that's the error, the percent error. Well, it would be, for me, it would be you'd take 100 times the absolute value of yk minus xk divided by the actual value of y. It's an absolute value. So again, it's a number that's greater than or equal to 0, and it's a percent. That's why I multiply times 100. A lot of people wouldn't have that column, and you don't have to. And if you can't find an explicit solution, you can't have an error column. You can't have these last three columns. You can't have the actual value of the function. You can't have the error, and you can't have the percent error. So these four columns are the big ones. The other three, I'm not going to fill those in because I don't want to punch the x's into a calculator anyway. But how do you fill in this table? So we started with initial data when k is 0. X sub 0 for us, our initial x coordinate was 1. Our initial y coordinate when k is 0, y sub 0. We were told x at 1, y at 1 is minus 1. So your initial data goes here and here. Okay. You can also go ahead and complete this column. So because we've picked a number of steps, we picked n is 4. We calculated delta x is 2 minus 1 over 4. So it's a quarter. And so our x's go up by 0.25 each time. So you just add 0.25 to the entry above it. In a spreadsheet, what this means is you would say that each cell in a spreadsheet, so for this column, you'd say each cell is 1 plus the cell above it and fill down. In this column, you would put your initial x value here. Then whether you calculate delta x by hand or have it calculated in a cell in your spreadsheet someplace, you would say this next entry is the previous entry plus delta x, and then you fill that down so that each entry is always the previous entry plus delta x. If you've done it correctly when you're at the number of steps you picked, 4 for us, you'll be at the x value for which you're interested in approximating the y value. Our goal is to fill in this column. And if we're really trying to approximate y when x is 2, what we're really after is this spot right here. But we have to calculate these along the way. How do we calculate those? Well, we keep using, I'm going to erase my error columns to give myself room, and I'm not going to fill them in anyway. But each time, the next y value is the previous y value plus the function that you've got evaluated at your previous x and y values, which you know, times delta x. So again, in our specific example, this is yk plus, we know this function in our example is xk minus yk times delta x. So this is the formula we're going to use. So that's why I've got an m of xk, yk column. So in our example, that's xk minus yk. This is the column that would change when you have different differential equations. Because this is the column that has to have a formula in it that corresponds to the m of xy that you've got. We had x minus y. So in the spreadsheet, it should take this cell, the xk cell, and subtract the yk cell. Now, this function could be arbitrarily bad. You could have dy dx equals some function of x and y, and that function could be pretty bad. So either you want, if it's pretty bad, you either want a calculator to do it or a computer. So in the book sometimes I write that you could do this by hand and calculator. So I mean, if this function were more complicated, or even if you just wanted to do it for worse step sizes, or so different ends, you might want to use a calculator to help you with the numbers. In fact, I'm not going to go very far. This is a long, tedious process to do by hand. And by hand and calculator, if that function were bad, it would take a long time. So this is why you really want to do this in a spreadsheet. Still, you can do a few steps by hand if the function is easy, which is what I'm about to do. And if it's more complicated, by hand and calculator. But if it's really complicated, or you've got a large number of steps, then you want to do this on a spreadsheet or on a programmable calculator that basically has tables or spreadsheets in it. So what do you do at this point? Whether you're on a spreadsheet, doing it by hand, you calculate this column, and it depends on what your function is. For us, it's this x value minus this y value. So here we would get 1 minus 1, which is 2. What do you do with that? Now you fill in these entries, and on a spreadsheet you would fill down. So you could fill this formula down. This column is always this minus this. Not for every differential equation, just for the one that corresponds to dy dx equals x minus y. For a different differential equation, you have to put in whatever formula corresponds to that and write equals, and then in place of xk and yk, refer to this cell and this cell and fill down. But now each next y entry is the previous y entry plus m of the previous x and y times delta x. So what goes right here for us? It is the previous y plus m of xk, yk, which is what's in this column, times delta x. And delta x is 0.25 for us. So we get, this is 0.5, and then minus 1, so we get minus 0.5. I need some more room. Let me spread this out some. And actually, I'm not going to do 4 steps anyway. So as I said, this gets pretty tedious pretty fast. So all right, so here we're getting, so this is 0.5 minus 1, so we get minus 0.5. And then what do? You just go on. If you're in a spreadsheet, you should have already filled down enough that it'll just go on. If you're doing it by hand, what do you do now? Well, now you've got the next xk and yk, but when k is 1 now. You've got x1 is 1.25, y1 is negative 0.5. You evaluate this, so it's this minus this. So we get 1.25 minus 0.5, so this is 1.75. And now that you've got that, you can fill in this, the y sub k when k is 2. So y sub 2, what is it? It's your previous y value. So the y value from your last cell minus 0.5 plus the m of xk, yk, 1.75, times your delta x, which is still 0.25. And you calculate this, and it goes here. And then you use this entry and this entry, and that would tell you this one. It's this minus this. And once you've got that, you fill in this position. This is the previous y value plus whatever value's in this column times delta x, and you just keep going. This is Euler's method. And you just have to know that for reasonable functions, and it's possible to say what reasonable means, but at the end of the day, basically reasonable means functions for which this is true, but it's for which the approximation is good, for which what I'm about to say is true, which is that if you take n to be really large, this is very accurate. So if you take the number of steps to be large, so a small delta x, this gets very accurate for lots and lots of differential equations. It's an easy method because it's just linear approximation over and over again. But even though it's easy, as you can see, even by hand, like right now, multiply those two together. Well, get out a calculator. I mean, you could do it, but 4 steps isn't many. You'd like to do 100 steps or 1,000 steps or 10,000 steps, or I think Excel's limit is 65,000 lines or something. But it's easy. It's easy to fill in the formulas. It's easy to fill down. And I'll say again that there are more accurate methods, but the formulas you fill in are much more complicated, much more. They're very difficult to remember. You really look them up once and then make a spreadsheet from it, or really it's programmed into calculators and computers. Runge-Kutta is a modified form of Runge-Kutta is what they use to do approximations to solutions, differential equations. All right, this is honestly all I want to say about Euler's method. It is a numerical method based on iterating linear approximation, but you chop the interval that you're doing linear approximation on into lots of little subintervals, and then you iterate linear approximation. That's Euler's method. There's a graphical method that's, in a sense, similar to Euler's method. It's like a lot of graphical methods. You can kind of see some cool things, but it's not, if you then kind of try to sketch solution curves on the graph, it's less accurate than Euler's method, or at least when I sketch them, it is. But still, it's an interesting topic, and it does provide some insight into how the solutions to a differential equation might change with the initial data. So let me briefly talk about slope fields. So we're looking at the same sort of differential equation, but now we don't necessarily start with initial data. We might, but one of the great things about slope fields, or nice things about them, is that they're a nice way of qualitatively seeing how solutions to differential equations or initial value problems depend on the initial data when you leave the differential equation itself fixed. So let's pick on the same differential equation, dy dx equals x minus y. And somehow we want to look at solutions to this graphically, regardless of what initial data we start with. And you may be thinking, sure, yeah, right. What do you do? Well, one thing you can do, and what slope fields are, is if you think about it, what this says, well, is that any solution to the differential equation satisfies this. But if y is a function of x, if you've got y as some function of x that satisfies this, then dy dx, this is the slope of the tangent line. Right? The derivatives. Slope of the tangent line to the graph. Or the solution. So A, or the solution. So this tells you what the slope of the tangent line, the solution, would be in terms of x and y. So in terms of the point that you're looking at. So what you do is you draw a bunch of little line segments at lots and lots of points, ideally, a bunch of little line segments that have the slope specified by the function that's over here. So m of xy, in our case, x minus y in the example, but in other cases it could be other things. And you draw a bunch of little line segments that have the slope specified by this function. And then it's almost like a connect the dots problem from when you were a kid, except then the dots were numbered and you just drew straight lines from one dot to the next. You have all these little line segments with some slope. And what you want to do is draw a smooth curve so that every time it hits one of those line segments, that line segment is tangent to the curve you're drawing. So the line segment kind of tells you which way the curve should go in each direction. Of course, there are a lot of empty spaces in between the line segments you draw, and then you have to kind of estimate a slope in between as you're drawing the curve. So it's very rough, but let's look at this one. So one way, of course you can have a computer draw lots and lots of little line segments, but let's, our function is m of xy equals x minus y. So what I want to do is at a bunch of point xy pairs, draw line segments that have this slope. So for instance, if I'm at 0, 0, m of 0, 0 is 0 minus 0. Well, that's 0. So at the point 0, 0, I want to draw a little line segment with slope 0. So here we are at 0, 0, and I draw a little line segment. If I were using paper, I would draw a smaller line segment, but so that you can see it, I'm drawing a fairly big one. What happens at 1, 1? At 1, 1, m of 1, 1 is 1 minus 1. Oh, that's 0. So at the point 1, 1, I also draw a little line segment with slope 0. So here I am at 1, 1. I draw a little line segment, slope 0. All right, what about at this point? Here we are at 1, 0. Well, m at 1, 0 is 1 minus 0. It's 1. So at this point, I want to draw a little line segment with slope 1. And you keep going. You'd like to draw a whole bunch of these, but it gets old really fast. You really want a computer to do it. Like at 2, here we are at 0, 2. So if this point is x is 0, y is 2, then m of xy right there. So I am using m for slope. M is kind of standard for slope. 0 minus 2. So I should have a line segment with slope minus 2. So a line segment with slope minus 2. And you keep doing this. You pick, I don't know how many you think is reasonable or how many your own instructor would think is reasonable. Certainly I wouldn't draw more than 10 of these by hand. This was not part of our slope field. Wait, you draw a bunch of these little line segments at a whole bunch of points, and that's called a slope field. Now, as you can see, I have not drawn enough for us to reasonably sketch any solution curves. So is there a way by hand to sketch little line segments in your slope field more quickly? Yes, but really, the answer is yes, and I'm going to tell you how. But really, you'd prefer to have a computer do this. It can draw, it can draw 10,000 of them faster than we can draw 5. But just so we can see by hand a little bit of what's going on, let me tell you one way to draw things a little faster. You can fix what you want the slope to be. So fix the value of m that you're after, and then draw a whole bunch of little line segments with that fixed slope. Like, suppose we want to look at all of those where m is 0, so where the slope is 0. That means, so we want x minus y to equal 0. That means that y has to equal x. What does that mean? It means that along the line where y equals x, all the points will give you points with slope, well, where the slope field has 0 slope. So you can just go ahead and indicate the line y equals x. So this is not a solution curve. This is just a curve. I'm drawing just a very fine dotted line because along that line, every single little line segment in our slope field has slope 0. So you draw this line segment, or this line, where all the slopes are 0, and then you just draw along that line a whole bunch of little line segments with slope 0. Great. That included our point 1, 1. Of course, I missed it now, but you can't draw a line segment everywhere, which is why I said when you're sketching solutions, you have to kind of estimate in between the points where you have line segments. You can fix m equals 1. And then you would have x minus y equals 1. That's the same as y equals x minus 1. This is a line with slope 1 and y-intercept minus 1. So it's this line. And along that line segment, we should have, along that line, which didn't look very linear over here, our slope field should consist of a bunch of little line segments of slope 1, which is the same as this slope. So it goes in the direction of the line, but that's unusual. Like these little line segments weren't right on top of the line. Let's do one more. When x plus y, or when m is 2, we would have x minus y equals 2. So that's y equals x minus 2. Again, it's a line of slope 1, but in y-intercept minus 2. So it's parallel to those lines. That distance is supposed to be the same as that. And now along that line, everything has slope 2. So all the little line segments in our slope field have slope 2. Anyway, using these curves or lines along which the slopes are constant can enable you to draw a whole bunch of line segments quickly. But again, you have to pick different m's, and it's not so fast, and you don't get that many. We give a name to these curves or lines along which the slopes are constant. They are called isoclines. That just means iso means it's a prefix meaning same, and clines inclination. So same slope. They're curves along which lines or curves along which you have the same slope. All those are supposed to be slope 0. And yeah, they're at least they're a device for helping you draw slope fields. So we haven't drawn many. Maybe I should draw one more just to have some vague hope of sketching a solution curve. We'll do one more isocline at minus 2. So when fix m at minus 2, we would get x minus y equals minus 2. That is y equals x plus 2. It's a line with slope 1, but y-intercept 2. Actually, let's go with 1. Minus 1, sorry. Let me go with slope minus 1, just for ease of drawing. So we get a line of slope 1 and y-intercept 1. So that's this line. The dotted lines are the isoclines. They are absolutely not solution curves. They are just, as far as we're concerned, they are just lines or curves that we're using to help us draw the slope field. And along here, we should have all slopes minus 1 along this isocline. So slope minus 1. Okay, what do you do with this? You can try to sketch solution curves now. We really don't have enough lines in our slope field, but you can kind of see, hopefully, that if you started with a curve here. So when I say start with a curve there, that means you're given some initial data. It tells you, this point is on our point that we care about. So maybe you're given that y at, so what does it look like I've got drawn there? Maybe that's y at minus a half equals a half. When x is minus a half, y is a half. So your solution is supposed to pass through. X is minus a half, y is a half, which to me looks like it's about here. Then you start drawing a solution curve there. And as I said, you try to draw a curve so that every time it hits one of these line segments, that line segment's tangent to it. And even when you're in between line segments, you try to draw a curve so that the tangents are kind of an average of the tangents you see nearby. So you can see here you should have a tangent that does that or does that, but when you get down here, it should be like this. So you can, hopefully you can kind of see, oh, okay, it should do this, and then it starts turning upward, and it looks like it would do this kind of thing. On the other hand, if you started with initial data that was down here, it looks like your curve would kind of do, well, it's without any in-between things, it's hard to know, but it looks like it would roughly do that. It looks like they're all roughly approaching this line. You try to draw curves that every time they hit a line segment, they have that slope, but when you're in between line segments, you kind of average your slopes and try to draw everything smoothly. If you had a bunch of these, and computers do draw a bunch, if you had a bunch of line segments, it is kind of cool just to start sketching on top of it. It is like a connect the dots problem. It's, and you can see when you do it how the different initial data lead to different solution curves, how the different initial data leads to different solution curves. It's a nice graphical method for kind of analyzing the behavior or seeing the qualitative behavior of one of these first order equations of the form dy dx equals a function of x and y. However, sketching these curves on a slope field is less accurate than doing Euler's method. And you have to have a computer to draw the slope field so that it's any good. And you kind of have to have you pretty much have to have a computer to do enough steps of Euler's method. So if you really want to know the numerical value of an approximation to a solution to an initial value problem, you'd rather use Euler's method. On the other hand, if what you're trying to do is visualize how the different solutions change when you change your initial data and just kind of the qualitative nature of the solutions, you'd rather stare at a slope field. All right, that's all I wanted to say on approximating solutions graphically and numerically. It's an interesting topic. It's not particularly easy to discuss on a blackboard. It'd be easier in a computer lab. Computers, in a way, doing either one of these on a spreadsheet is almost, or using a spreadsheet for Euler's method or using slope fields is almost, I don't want to say silly, but you can just ask the computer these days to numerically, if you're going to use a computer to do the spreadsheet, you can just ask the computer for the numeric approximation to the solution. It'll do Runge-Kutta, so a numerical method roughly like Euler's method, it'll do it behind the scenes. But is there some value to your knowing what it's doing? Yeah, probably. It's always nice to have some vague idea of what the computer's doing when it's generating answers for you. And you could also have the computer generate the slope fields for you, or for that matter, just sketch a whole bunch of solution curves for you. To sketch the solution curves, it will use Runge-Kutta and evaluate at a lot of points. To do the slope fields, it does what we were just doing by hand, just a lot faster. So, all right, I'm going to leave it at that.